Good morning, good afternoon to everybody. It's a pleasure to introduce Jacob Tsimerman, our MCA Prize awardee. He's now going to deliver the prize lecture. And Jacob made his PhD in Princeton in 2011, and now he's currently in the associate professor in the University of Toronto. And he's going to speak about canonical height of Shimura varieties and the Andre-Oort conjecture. Thank you very much, Jacob, to be here. And go ahead.
Thank you. Thank you very much for having me. I have to apologize to everyone. I had my wisdom teeth removed on Monday, so I look a bit funny and I'm going to sound a bit funny. If anything is unclear because of the way I'm speaking, in addition to my usual issues, please do interrupt me and let me know. All right, let me try and share my screen here. Okay, is this visible? Perfect. All right, so everything I want to talk about today, the new results at least, are going to be joint with Jonathan Pila and Anand Shankar. And I want to speak about some new results on the Andre-Oort conjecture. So just to begin with, to give a little bit of an introduction to the problem, let me just talk about a motivating problem for it, which is Lang's conjecture in a much more familiar setting. So the simplest case of it is we just start with C star squared. So the punctured plane, 2 copies of it, and we take an algebraic curve inside there, which you can think of explicitly as some polynomial in x, y, and their inverses. And the question that Lang posed and answered is which such algebraic curves, which such polynomial relations contain infinitely many solutions with both x and y being roots of unity. So it's a certain arithmetically interesting class of points. And you want to know what kind of relation can be satisfied by infinitely many of them. Now, of course, something that comes to mind is multiplicative relation. Roots of unity are essentially defined to satisfy multiplicative relation. So you can pick 2 integers m and n, and just specify that x to the m times y to the n is some root of unity. And this is going to satisfy the condition. And the theorem that Lang proved is, in fact, this is all of them. So if you have any algebraic relation satisfied by roots of unity, it must be multiplicative in nature. Okay. Now, if you want to generalize this to higher dimensional settings, you have to be a little bit careful, because even if you're a very, very strange surface, say in 3 space, nothing to do with roots of unity, you might contain a curve, for example, the diagonal curve x equals y equals z, and that will contain infinitely many solutions in roots of unity. And so what you do is you define these special subvarieties called torsion cosets. Essentially, you look at multiplicative subgroups, and you allow translation by torsion points. So essentially, irreducible components of multiplicative subgroups. And then if you have a variety in some higher dimensional multiplicative groups, you start at the n. If its dimension is bigger than 1, it could contain positive dimensional torsion cosets, excuse me, and those could be the source of your torsion points. And so the theorem, conjectured by Lang, proved by Raynaud, and since then proved many more times using various methods. This is sort of a test problem for many other generalizations, but Raynaud proved it first. And the theorem is that the way to state it is that you contain finitely many maximal torsion cosets. Okay, so another way to say it is that if you take a bunch of these torsion cosets, union them, and take their Zariski closure, you end up with more torsion cosets. You sort of can't leave the world of torsion cosets by taking Zariski closures. Okay, so this kind of setup where you have some sort of ambient space, you have some special structure, in this case, the group structure, giving you special points and special subvarieties. And you ask for this sort of no coincidence result, this sort of falls under unlikely intersection, sort of if you contain infinitely many such points, there must be a reason for it. This result, this kind of structure generalizes to many other settings. One sort of natural generalization, which I won't speak too much about, is to just replace the torus by an abelian variety. So if you take an abelian variety, It can be over a number of fields, but it doesn't have to be. Just any complex abelian variety is fine. You have abelian subvarieties. You have torsion points, so you can translate and get torsion cosets. You can talk about torsion points just the same. And you have the same theorem actually proven by Raynaud as well, using similar methods, though it's a slightly more complicated framework. That if you have, oh, sorry, this is misstated. This is V in A is what it should say. Then V contains finitely many maximal torsion cosets. Interestingly enough, I copied the slides from many other talks, so I must have had the same typo carrying around with me for a few years now. I wonder if I remember to change it this time. Okay, so let's move on to the setting of interest after that introduction. So the primary setting that I wish to speak about is that of Shimura varieties. So I'll speak a little bit more precisely about what they are in a minute. But for now, let's speak rather informally. So a Shimura variety, at least its complex points, can be described as some kind of symmetric space H modulo some kind of discrete group gamma. And I'll give a few familiar examples in a minute. But Shimura varieties contain the same kind of setup. They don't have a multiplicative structure or a group structure, but this it's still sort of lurking in the background. So you still get the set of special points called CM points, CM standing for complex multiplication, which are the analog of torsion points in this setting. And you have these special subvarieties, which are kind of Shimura subvarieties in a sense, which I'll describe. And these are extremely interesting for various arithmetic reasons. And the conjectured sort of separately by Andre and Oort, is the same, that if you have a subvariety of a Shimura variety, it contains finitely many maximal special subvarieties. So essentially describing the algebraic relation between CM points in a Shimura variety. They're essentially all encapsulated by these special subvarieties. Okay, so that's the conjecture. There's been a bunch of partial results on it. So to summarize them, there's sort of more than this, but this is kind of my selection of the highlights. Sorry if I left anyone out, but I think the first big progress on it was due to Andre, who did the case of y1 squared. And then based on an idea of Eriksoven over many years, work by Klingler, Umo, and Yefev, established the conjecture conditionally on the Riemann hypothesis. And like almost every other instance of a theorem that you see conditional on the Riemann hypothesis, the reason you need the Riemann hypothesis is for the existence of small split primes. So I'm not going to go into the details of this proof, but essentially the reason you want GRH is to have low degree Hecke correspondences. And then they play with those, and as long as they're sort of low degree, things don't get too crazy. Okay, that's barely even a summary, just a few words about what goes into it. Then in 2011, Pila came up with a different strategy based on his work with Zanier. And he unconditionally established the case of y1 to the n, so arbitrary products of modular curves. And then the strategy was pushed over the course of many years, and I'll describe it in a minute. And the latest result in 2016, I think, depending how you count, based on joint work of myself and Pila, and then a paper of myself, I established that the conjecture is true for AG, for the Siegel modular variety. So it's in this interesting state now, this conjecture, where essentially you have it for all Shimura varieties of abelian type, everything coming from the primary example of abelian varieties and their moduli. And what's left are the so-called exceptional Shimura varieties, the Shimura varieties of exceptional type, which are very mysterious for sort of a variety of reasons. I'll go into some of them. But so the theorem I want to talk about is that we can now prove the Andre-Oort conjecture for any Shimura variety, including the exceptional ones, as long as it's proper. And I'll explain the reason why we need the properness hypothesis. And there's currently work in progress to remove this hypothesis. And I'll go into that a little bit later. All right, so that's sort of the summary of what I want to talk about. So let me now, as promised, just recall some examples of Shimura varieties. Of course, all these examples will be about the classical Shimura varieties, which are not the subject of this talk. all of these Shimura varieties are going to have modular interpretation, and they're going to be very nice to describe from that point of view, which of course is partly why the theorem was easier in that, as many theorems are in that setting. Nonetheless, to get a sense of how these things look, the classic example is the modular curve. So if you think of it from an algebraic geometric point of view, you can think of it as moduli space of elliptic curves. You can fiddle around with adjectives here. I'm not going to go into that. And over the complex numbers is just the usual upper half plane modulo the action of SO2Z, giving you this transcendental uniformization map. What are the special points? Well, from the perspective of moduli theory, it's just those elliptic curves with extra endomorphisms, hence the term complex multiplication. And from the perspective of uniformization, you also have a nice description. It's just those points, in the upper half plane whose degree over Q is 2. So the quadratic irrationals, basically. So a very simple description from both points of view. Of course, they're easier to describe in coordinates over here. Once you look at their J invariants, you get much more complicated algebraic numbers that are much less explicit. And what are the special curves in Y1 squared? So what are sort of its Shimura subvarieties? Well, this is one of the cases where you can describe them very explicitly. Usually you can't, it's much harder. But in this case, it's very simple. You either take a fiber over a special point in one or the other coordinate, or you have these Hecker correspondences, where from the perspective of moduli theory, it just records pairs of elliptic curves with an isogeny between them, or which are isogynous, depending how you think about it, of a certain degree. So here I'm specifying the kernel of the isogeny. And from the perspective of the upper half plane, I didn't write this, but you can think of this as the graph of multiplication by n. It in fact descends to a nice algebraic curve in Y1. Okay, and so Andre's theorem from this perspective is that if you have a curve in Y1 squared, and it contains infinitely many CM points, i.e. A point both of whose coordinates are these CM points here, then that curve is special. It's one of these three families of curves. And recently there's been some work, well, I guess it's not so recent anymore, but there was some work doing this effectively. So given the curve, you can specify sort of how many points there are and try to give an algorithm to find the points, which is a much stronger kind of result. And in all of these kinds of questions, one of the main difficulties in making this kind of work effective is always the Siegel zero. So it's the same reason that the class number formula is ineffective and all this kind of stuff. Okay, but I'm going on a tangent again. Okay, so let me describe a little bit less explicitly, because it is less explicit, the case of AG. So this is just the higher dimensional case of Y1. Instead of parameterizing elliptic curves, we're now going to parameterize principally polarized abelian varieties. You can specify some extra structure, but I'm not going to go into that. So now we have this higher dimensional analog of the upper half plane, which is the Siegel upper half plane, given by sort of symmetric G by G matrices, whose positive part is positive definite. If you specialize this to G equals 1, you can see pretty easily you recover the usual upper half plane. And the complex points of AG very similarly can be described as a quotient of Siegel space by not SL2, but SP2GZ. The reason it's symplectic and not all endomorphisms is because you have a V pairing, which you have to respect from the moduli perspective. Okay, so the special points you can also describe fairly explicitly. From a moduli perspective, they're just those CM points. So they're just those points corresponding to abelian varieties which contain a certain endomorphism ring. Now it's not enough to specify extra endomorphisms. You have to have enough endomorphisms. So the way to say this is you have a Q algebra of degree 2G. This is maximal possible acting on your abelian variety. Sort of this is big enough to rigidify the moduli problem, which is why this is the right number. And likewise, you can describe them inside Siegel space. It's a little bit trickier to describe them all very explicitly, but they're at least contained in this very nice simple set where you look at points with degree over Q, or is it at most 2G in Siegel space. And you can actually, you can say fairly explicitly what this set is in the Siegel upper half plane. Okay, now it's much harder to classify the special subvarieties in AG. I'm not sure there's a, well, I'm not an expert, but based on what I've seen, I think it'd be hard to give a complete classification. But here are some prominent examples. One example is you can look at the gth symmetric power of the modular curve. So from a moduli perspective, this is those abelian varieties that split as a direct sum of G elliptic curves. You can fix a totally real field F and of degree G, say, and you have these Hilbert modular varieties. From a symmetric space perspective, here's what it is. It's sort of the gth power of the upper half plane mod this lattice, SO2OF, where the embedding is via all the different real embeddings of F. And from a moduli perspective, this is just those abelian varieties with endomorphisms by F. And then you can fix other endomorphism structures. You can do more complicated things. You can do things that don't correspond very easily to endomorphism structures, sort of the non-PEL type Shimura varieties. So there's a big list of them. It's kind of hard to describe precisely, but this maybe hopefully gives you a flavor of the kinds of things we're talking about. Okay, so now comes the dreaded GX notation, which I've hated for many years until I had to deal with this problem, and then I had to reluctantly admit it's kind of useful. So how do we talk about general Shimura varieties? Because we no longer have a sort of a moduli theory to speak of. In fact, it's an important open problem whether you sort of have families over exceptional type Shimura varieties, realizing them as moduli spaces of an appropriate kind, which is not known for any exceptional Shimura variety. Part of the reason is because all the exceptional groups have such high dimension that you sort of can't get your hands dirty even on the simple case. Anyways, how do we talk about general Shimura varieties? Well, there's three pieces of data which go into a general Shimura variety. First, you have to pick a reductive algebraic group over Q, call that G. Then you fix this funny little creature. X is a conjugacy class, a single conjugacy class of maps from the Deligne torus, which is a simple object. There's the restriction of GM from C to R, to the real points of the groups. This is really an object defined over the reals. And this might look unfamiliar, but X is sort of the symmetric space that we're all used to. In the upper half plane setting with SL2, how do you understand the bijection between X and the upper half plane? Well, around any point in the upper half plane, there's a subgroup of SL2 corresponding to rotations around that point. And that subgroup is precisely the image of the corresponding H. So in general, it's kind of a similar story where around every point in your symmetric space, you have an S1 in your group, which rotates by that complex number. And that's what this H is. Okay, hopefully that gives you some kind of idea how to go back and forth between them. And then you fix this kind of annoying piece of data, a compact open subgroup of the adelic points of G. Okay, this is really to keep track of which lattice you're quotienting out by. So you can write the actual complex points of your Shimura variety in this sort of fancy adelic way. You take X, you cross by the adelic points, you multiply by K on the right and by GQ, by the Q points on the left. It's some fancy thing. You don't have to do this. It's just nicer to do this. If you prefer, you could instead look at X modulo sort of an integral lattice inside G. The reason this is really nicer to think about comes along when you're interested in sort of subtle arithmetic properties, such as Galois group actions and things like that. Then keeping track of things in this language becomes quite useful. If you care about things like functional transcendence or anything like that, more geometric properties, this becomes more of a burden than anything else. But for arithmetic, which we're going to be doing, this is quite useful. Now, what are the exceptional Shimura varieties? So those that don't embed into AG. So given this data, by the way, there's a bunch of axioms you have to satisfy that I haven't mentioned that I'm not going to go into, the Shimura axioms. But given this data, it becomes quite natural to talk about maps between Shimura varieties. It's just maps between groups, which send these conjugacy classes to each other, and which send these compact open subgroups to each other. It's quite natural. And so now you can talk about, well, okay, you have this big, important Shimura variety, AG. What are the guys that don't map to it, that don't just come from that one? So it's complicated because there are many, many reductive groups over Q, many more than over C. You have various twisted forms. But in fact, you can almost describe the answer over C without worrying about Q types. So the two exceptional groups, E6 and E7, all Q forms of those are non-abelian. They don't come from AG. And then you can play some tricks with orthogonal groups to get non-abelian things as well. I'm not going to go into it. But this essentially tells you which Shimura varieties are exceptional. Now, how do we think of CM points from this perspective? Well, it's actually quite simple. So CM points are sort of like the zero-dimensional Shimura varieties. So when is this X just a collection of points? Well, when this conjugacy class here is just a single element, because this is a real thing. It's either a point or it's got some dimension to it. In other words, it's when this G is abelian. So CM points just correspond to those maps from S to GR whose image lies inside some subtorus T of G. Now, there's an important thing to keep in mind here. Over the reals, of course, this is always true. The image of this is already a torus. CM points correspond to those maps H such that the image lies inside some rational torus T inside your group G. And that's the special points we're interested in. Okay, now there's a theorem due to many, many people, Bailey-Borel originally, and then Milne based on his work with Xi. Borovoy did a bunch of work also. They used theorems of Kazhdan. It's a long project that was settled in the 80s to essentially take these Shimura varieties, which remember a priori are just defined as complex manifolds, nothing more. And first of all, give them the structure of an algebraic variety. This is done by Bailey and Borel. And second of all, to give them canonical models. So to give them models not just over C, but to show that they have natural models over number fields, over some reflex field E of GX that I won't talk about very much. And what do you want from this kind of model? Well, you want the Galois action on CM points to be described by a certain reciprocity law. Essentially, the subject came out of generalizations of complex multiplication, the formula for elliptic curves. People realized that the CM points, the Galois action on them, record certain class field theory mappings. And so that sort of motivated this whole theory. Now, over AG or over any moduli problem, this is all not trivial, but much, much, much easier because the moduli problems can all be defined over number fields themselves. Everything is canonical and natural. Things work out great. Over the exceptional Shimura varieties, you sort of have to start with your complex manifold and go from there. So through a lot of work, using some rigidity properties, understanding CM points, this was proven. Now, I want to mention here a certain duality is going to come up again that came up in this problem and will come up for us later. You have this very lovely duality which works in your favor, that if you have a general Shimura variety, one of two things happens. Either it's abelian type, so it comes from AG. You can think about it in terms of abelian varieties in some very useful way, and then you're golden. Or if it's not, at the very least, things are very rigid. So you have results like Margulis super rigidity, you have various differential geometry rigidity results, all sorts of methods like that. And those are extremely useful when tackling such problems. So this is a very common duality. It's going to come up for us. It's going to come up in work we quote as well. So I'll mention that later when it comes up. Okay, I'm going very slowly. I'm not going to spend too much time on this because I want to speak about the new ingredients we're sort of mostly focused on. But just to give a sense of the general strategy for the Andre-Oort conjecture employed by Pillay and Zanier, let me describe the strategy in the case of the original problem I talked about, length conjecture for n equals 2. So just to remind you, we're talking about this problem here. If you have a curve inside C star squared, it contains infinitely many roots of unity. It's got to be of this form. Okay. So let Z be such a curve, and suppose you have a bunch of torsion points on it, Wi. The torsion points are all defined over Q bar. They're all algebraic, so Z is algebraic. And for simplicity, I'm going to assume Z is defined over Q. It's not going to change anything, but might make things a bit simpler. Now, the idea for the setup is to actually look at this transcendental uniformization map, right? And even though it's transcendental, the torsion points, the special points, behave very nicely in both worlds. Here, they're roots of unity. And here, they're just rational numbers, because the root of unity is just e to the power of 2 pi I times a rational number. OK, so now the proof comes from comparing a lower bound to an upper bound and getting a contradiction. And what these bounds are for are you count the number of such points. You count how many roots of unity you have of order n. So on the one hand, if you have one such point, you have the entire Galois orbit of that point as well. And roots of unity have huge Galois orbits. In fact, all the ones of order n in dimension 1 are Galois conjugate to each other. And so automatically, if you have one such point, you have phi of n such points. On the other hand, this is getting a little subtler now. This is where the tricky part comes in. You first show that if you're not a torus coset, if you're not multiplicative, then if you pull back to C squared under this log map, you don't get something algebraic. Note that for if you are a torus coset, if you're like x to the m, y to the n equals something, and you take logs, you get something linear, so definitely algebraic. But if you're not a torus coset, you show your inverse image is not algebraic. Okay, there's some kind of theory there that's not totally obvious, but let's accept that for now. And then you show that since you're transcendental, you can't contain many rational points, which is, again, just a theorem now about Diophantine approximation, basically. It's transcendental sets containing rational points. You show that can't happen. You give this explicit bound of n to the epsilon. And that's a contradiction because phi of n is very big. It's close to n, much bigger than n to the epsilon. So what's the structure of the argument? Well, you count how many special points you have of a certain type, a certain complexity, in this case, the order of the point. You get a lower bound from Galois theory, and you get an upper bound by first showing a statement in functional transcendence, and then using that transcendence to obtain bounds on counts of rational points. So let's summarize this in the general case. How would this go? You have this kind of uniformization. Suppose you have a subvariety that has a risky dense set of special points. We want to show that it's special in some way. So first we pull it back and we show it contains many points which are rational, not quite rational, but of low degree. Like for the upper half plane, you will get quadratic irrationals. It's close enough. On the other hand, so you have many such points because of the Galois action. On the other hand, you can't contain many such points unless your inverse image actually contains algebraic subvarieties. So this is a key ingredient. This is well, I'll mention where this word comes from. But the point is downstairs you're algebraic, upstairs you're transcendental, and the only way for a transcendental set to have many rational points is to contain algebraic subvarieties. Okay, and then you show that this only happens if you're sort of algebraic upstairs and downstairs. This only happens if you're a special subvariety. So to summarize the fundamental ingredients here, we go into the proof. First of all, you have what's known as the Pila-Wilke theorem, that if you have a real analytic variety that contains many rational points, it has to be algebraic. There's no other choice. You have a functional transcendence ingredient, which is basically saying that the algebraic structures upstairs and downstairs, under this transcendental uniformization map, they don't interact with each other at all. There's no relation except what's mandated by these weakly special subvarieties. They're sort of the one being that can exist in both worlds. Other than that, these algebraic structures don't intersect with each other at all, don't interact at all. There are precise statements to this account. I've spoken about this many times. I'm going to not speak about this this lecture, but there's many fantastic talks about X-Chanual theorems, out there recent works on mixed Hodge variations and all sorts of stuff that I can mention later if someone's interested. And the last ingredient, which is the one that's missing, so I'm going to focus on that one, is this Galois orbit business. Now, this was very easy for roots of unity because the Galois orbits, the Galois action is very easy to describe. It just raises the root of unity to a certain power. In general, though, you have to show that if you have a special point, then the Galois orbit of that point is big compared to the complexity of the point. I'll mention what that is a little bit later. For roots of unity, it's just the order of the point, but there's some sort of measure of complexity in general. So this is the last sort of missing ingredient. It's been known for a while that these two are done, and if you can prove large Galois orbits, then you get the Andre-Oort conjecture. So I'm going to focus on this. Okay, so in fact, we're going to reduce to another problem, and I'm finally going to, in a couple of slides, get to the first part of my title, which is heights. We're going to reduce another thing, which is a height bound for a special point. So let me explain how this goes in the AG setup. So remember, you want to show that special points have large Galois orbits. So suppose you have very small Galois orbits. Just for simplicity, assume you actually have a special point defined over Q. And let's assume for simplicity again that it's endomorphism ring, which a priori can be some Q algebra thing. Let's assume it's just the ring of integers in some CM field. Okay, what we're going to do is we're going to look at the family of all CM points with that same endomorphism algebra. And it's known that these guys all behave pretty similarly. It can be shown pretty straightforwardly that they all have basically the same Galois orbit, and they all have basically the same height. Now, Masser-Wurst-Holes prove that if the heights of these points are small, then there must exist low-degree isogenies between them, but there just aren't enough low-degree isogenies if you count subgroups. It's a very simple combinatorial problem. And so that shows that you must have not been defined over Q, i.e. you must have had large Galois orbits. And how do you show the height bound? How do you show this ingredient, that the heights of these points are small? Well, that follows quite simply from a very deep result, the average Kolmez conjecture, which tells you precisely what the Faultings heights of CM points are. This is not quite established, but an average version of it is established, which is enough to get bounds. This has two independent proofs by Andre-Oort, Gore, and Howard Matapusipera, and Yuan and Zhang. Okay, so I'm not going to talk about that basically at all. Neither of these two ingredients generalizes to arbitrary Shimura varieties. Masser and Wurst-Holes require heavily abelian varieties themselves, and there's no Kolmez conjecture. There's not even a Faultings height in exceptional Shimura varieties. Right, but recently, this first step, the reductor to the height bound, was established by Binyamini, Schmidt, and Yafaev based on a breakthrough of Binyamini. And very briefly, the way they work is what they do is, whoa, there should be a cross, excuse me. They look at the transcendental graph of the uniformization map. And on that graph, which is very transcendental, you have a bunch of algebraic points given by CM points. Now, what you'd like to do is do the same stuff Pile-Wilke did. Show that, well, you can't have many CM points because it's transcendental, and conclude that heights, sorry. Sorry, since the heights are small, if you assume the heights are small, you can't have many CM points, and so the degree must be quite large. Okay, however, you need something much stronger than what Pile and Wilke gave you, and that's provided by recent results of Binyamini, and he got much, much stronger bounds. And just to summarize them, I'm not gonna go into the details. His bounds constitute improvements in two major directions. First of all, instead of sub-exponential bounds in the height, he gets polylog bounds. So he gets log t to the O of 1 as opposed to t to the epsilon for the number of points. So what Pile and Wilke got. And also, this is, I would say, I mean, they're both very impressive, but this is an even more crucial improvement, which is that Pila and Wilkie could really effectively only work with a fixed number field. Okay, you can work with all points of a bounded fixed degree by taking, say, the characteristic polynomial of that point. But if the degree really grows, Pila and Wilkie's method just doesn't work very well. But Bignamini, adapting a method of 2 and Siegel, manages to get polynomial bounds in the degrees of the algebraic points as well. So you get a much, much more powerful theorem that allows you to count not just rational points, but truly algebraic points of varying degree. And using this, you can establish the reduction. Now, I want to mention, excuse me. I want to mention that Bignamini works in a far more specialized setting than Pila and Wilkie, which is why he gets more powerful results. Pila and Wilkie work in the general context of an arbitrary O minimal structure. So they work with transcendental functions far and wide. Bignamini, to get stronger results, he restricts specifically to transcendental functions which are obtained by algebraic foliations defined over number fields. So he restricts to a much more specialized setting, which nonetheless is sufficient to handle a lot of interesting cases. And as a reward, he gets these much more powerful results. Okay, so finally, we sort of arrive at this problem that I'm really genuinely going to talk about, which is obtaining height bounds for special points. So to set up the question, let S be a Shimura variety as before. Take any logarithmic V height on S. They're all the same up to an additive O of 1 factor anyways, so who cares? Just pick your favorite one. And now I'm going to write this down here. You can ignore it if you want, but if you have a CM point, what is this complexity? Well, you can define it to be this quantity. It's sort of essentially the discriminant of your splitting field times the index of the compact subgroup you get inside the maximal compact. Okay, it's some kind of notion of complexity. And the theorem is that for a proper Shimura variety, as you vary over CM points, the logarithmic V height is subpolynomial in the discriminant. Okay, this is exactly what Bignamini, Schmidt, and Yafeev need in the reduction. All right, so let me now switch gears and describe how we obtain this proof. So the main idea, and hopefully this will have applications elsewhere, is, okay, so here I said it doesn't matter which V height you pick, and that's true, but it's kind of hard to work with arbitrary V heights. Arbitrary V heights are defined up to O of 1, and they're very inexplicit things. In fact, for the case of AG itself, for abelian varieties, this is precisely why Faultings defined the Faultings height, which is an honest-to-goodness canonical height function on abelian varieties, on the moduli space, excuse me. It's also a V height, so if you only care about the loose properties of V heights, you get them, but you get a precise number to work with and compare, and he uses this to great effect originally in his proof of the Mordell conjecture. So our first idea is to do something similar for arbitrary Shimura varieties. So given an automorphic line bundle on a Shimura variety, we want to define a canonical height function, truly fully canonical height function with good functoriality properties. So essentially, if you have a map of Shimura varieties, then the height function should pull back in the sort of natural way. And this would be a generalization of Faultings height on honest-to-goodness AG. And then the problem, once we define this, is to bound this height when you evaluate it on CM points. But now, since this height function is canonical, you get a problem essentially intrinsic to this tori, to these tori that show up. Essentially, what you can do is you can take the CM point out of the Shimura variety, look at it all by itself, and try to see what the problem means there. Now, if you do that, the problem is still complicated. We still can't really, from first principles, say anything about it. But now we have this fantastic input where we already know that the theorem is true for all CM points in AG. So this gives us a huge amount of information. We get a huge amount of bounds on heights of automorphic line bundles on these CM points, these zero-dimensional Shimura varieties. And the idea is from that, just taking linear relations to deduce the height bounds on that show up from arbitrary Shimura varieties. Okay, and so yeah, to emphasize again, because for every CM point, we're going to be sort of pulling it out and doing a different comparison. If we work with an arbitrary V height, we're going to get a different O of 1 per point. And that's sort of, it doesn't add up to anything when comparing different points to each other. So it really is crucial we get a canonical height bound here, a canonical height function, excuse me. I'm sort of the most lazy, hooray for cheating person around. So I really did test this assumption and try to make the proof work by just picking arbitrary V heights. It really seems to need a canonical height function. Made me appreciate the Faultings height a lot more. Okay, so let me now describe in sort of combinatorial language what sort of really shows up for arbitrary CM points, because people are really, at least for me, I was really used to thinking about CM abelian varieties and kind of ignoring arbitrary CM points. Now, CM abelian varieties are given by CM types, as those familiar will know. And there's this term coined by Michael Harris called a partial CM type, which is sufficient to study all CM points arising in arbitrary Shimura varieties. So the way it works is the following. You pick a CM field, and now instead of a full CM type, you just take a subset of embeddings into Q bar, which doesn't intersect its conjugate. So for a full CM type, out of every pair of complex conjugate embeddings, you would pick one. Here, you're allowed to leave some pairs out completely and take one from whichever pairs you want. This is called a partial CM type. Using this data, just like for abelian varieties, you can define a CM point. You take your torus to be, there's many choices, but I'm going to just pick one, the restriction of scalars from your CM field, Q of GM. And you get, now a conjugacy class of maps is just a map for tori, because tori are abelian. And so you get this map, which is somehow defined by, in terms of this partial CM type. So you get a canonical Shimura variety. You also get a canonical automorphic line bundle, where you sort of take the co-character corresponding to this partial CM type. I know I'm skipping a bunch of details, but it's really, I just want to show that it's all very sort of group theoretic in terms of tori in these cases. And now we need to bound this corresponding canonical height function, which I haven't defined for you yet, but I promise I will do. And what you can use is the fact that for AG, essentially what you get is the case where phi is a full CM type. Whenever phi is a full CM type, we can bound this function, and we want to relate it to the partial CM types. Now, Deligne had a brilliant idea to deal with this problem 50 years ago when he was dealing with a different question. He was trying to show that all CM points, all zero-dimensional Shimura varieties, in fact, come from abelian motifs. They're related to abelian varieties. And okay, this is some fancy statement. What it amounted to was essentially, given a partial CM type, he had to construct out of it some kind of complete CM type with which to get some sort of embedding. So if one deconstructs his work, what does he do? Well, he makes the following brilliant observation. Suppose you have a fixed totally real field and a bunch of different CM extensions of it, K1 through Kn, quadratic totally imaginary extensions. And let's say each one of them has a partial CM type on it. So for every embedding of F, each Ki, each of these phi i's has at most one embedding over it. And let's assume that in fact, each of these are partial, but together they sort of partition all the embeddings of F. For every embedding of F into Q bar, there's exactly one I, such that phi I contains an embedding of Ki above that particular embedding. We get a bunch of partial CM types coming from different CM extensions. And so now we do the following thing. We take the join of all of these CM fields. We look at the field they generate. This will be a field of degree 2 to the n over F. It will still be a CM field. We call that K total. And now we'll let phi total just be the union of the partial CM types induced from the phi I. So what do I mean by this inverse image? I just mean look at all embeddings of K tot, which on K sub I restrict to something in phi I. And if you do that, it's not very hard to see that this phi tot actually gives you a full CM type. So if you have a bunch of different partial CM types, you can put them together in this way to get an honest to goodness CM type, and then that's something which occurs in AG. So if you translate this to the language of these canonical heights that I've been talking about, you do some bookkeeping. What this amounts to is the following very simple formula, that if you sum the height functions corresponding to these partial CM types on the fields K sub I, what you get is the height function corresponding to this full CM type, phi tot, and this can be bounded by the resultant AG. This is just the Faultings height of some abelian variety. Okay, how do you use this? Well, the point is that given the field F, there's actually tons of CM extensions floating around. The easiest way to see this is just take F, take a big enough honest to goodness prime, and adjoin the square root of its negative. For almost all primes, this would be a CM extension of F. So you have tons of CM extensions floating around. And so you have lots of ways to combine heights of partial CM types to get heights of full CM types. And it's pretty easy to just take linear relations and deduce a bound for an individual one of these from bounds for all of these. And so that's basically how the proof goes once you have the canonical height functions. You use this idea of Deligne to relate partial CM types to full CM types. Essentially, in the vector space generated by these guys, full CM types span, and so you can just extract out the bounds, the individual bounds that you're looking for. Okay, so all that's great, and that's all going to happen once we actually construct the canonical height. So in fact, what happened was everything up to this point of the proof, so the previous page, was done a year ago. And then it turned out that making this canonical height is a lot harder than it seemed. And in fact, uses a lot of very recent results in relative p-adic Hodge theory. So let me move to a sort of more technical portion of the talk. I know it's been a little bit technical already. But let's describe how we actually construct this canonical height and some of the issues that arise. So let's recall the story. We have a Shimura variety. We have an automorphic line bundle on it. Remember, this is an object which starts life purely over the complex numbers and then becomes algebraic and descends to a number field using very difficult work by Milne and collaborators. So it's extremely hard to get a concrete handle on this creature. Oops. To define a canonical height on a line bundle, it by now pretty well understood that what the right thing to do is at every place, Archimedean and non-Archimedean alike, you have to put some sort of metric on it. So the Archimedean place, you put a continuous metric of some kind. At non-Archimedean places, you have to put some kind of smooth metric for whatever that means. And they have to glue up. So our job basically becomes at every finite place to assign metrics on these line bundles. At the Archimedean places, by the way, the problem is very simple. We just use regular old Hodge theory and use the Hodge metric. So this is a very well classical understood sort of subject. There's no issues here. The finite places, it's very hard because again, this descends to a number field very indirectly. And so you sort of know this object exists, but you have very hard time to understand what to do with it. So what's the approach we take? Well, to start with, automorphic line bundles are too hard. We don't know directly how to see anything inside them. So to begin, we instead look at local systems, find a rational representation of our group. Then the Riemann-Hilbert correspondence will give you a vector bundle with a Hodge filtration on it. And we're going to find our automorphic line bundle in some graded piece of this Hodge filtration. So essentially, instead of automorphic line bundles, we're going to work purely with local systems and the Riemann-Hilbert correspondence. Now, the nice thing about this is that recent work of Lu Zhu and then subsequent work with Diao and Len, all strongly influenced by the sort of defining work of Schulze, they actually managed to construct a p-adic Riemann-Hilbert correspondence. So if you start with a p-adic local system, a genuine étale local system now, they give a vector bundle on the corresponding algebraic variety over QP, which I'm going to call V sub P de Rham. This is their notation. So classic Riemann-Hilbert is V de Rham, and this p-adic Riemann-Hilbert is V sub P de Rham. And moreover, for Shimura varieties, using this rigidity, once again, very crucially, they essentially follow the proof of Milne through again. They show that this p-adic Riemann-Hilbert correspondence is compatible with the usual Riemann-Hilbert correspondence. So basically, you can start with a local system over Z, just given by a rational representation of your group. Then you can do two things. On the one hand, you can immediately analytify with classical Riemann-Hilbert. That gives you some vector bundle. You can show that's algebraic, and then you can base change to QP bar. On the other hand, you can first induce an étale p-adic local system and apply the p-adic Riemann-Hilbert correspondence. So you can analytify, these sound similar, but they're actually very different constructions because you're analytifying over C on the one hand and over QP on the other, very different kind of objects. Nonetheless, they show that in the specific case of Shimura varieties with these vector bundles, you get something compatible. Okay, so what does this do sort of under the hood? This is not going to be, so this is kind of speculative on my part. But what's happening under the hood here is the following. Essentially, we're trying to give heights, sort of p-adic norms on the Hodge-Tate realizations of representations of local Galois groups. So if you start with a local field and you let L be a Hodge-Tate representation of GK over ZP, now in practice L will be de Rham or even crystalline, but all you need is Hodge-Tate to make these constructions. Let me speak in those words. Then it's known that if you tensor with CP, and you look at various twists and take Galois group invariants, you get sort of enough invariance. That's what it means to be Hodge-Tate. Now, since you're tensoring with twists of CP, then since L is a lattice, the vector space L tensor CP, twisted or not, has a very natural metric on it. And that induces a metric on this Hodge-Tate, this nth Hodge-Tate piece of it. This turns out to be the wrong metric. Instead, what you want to do, we define it to be the intrinsic norm on L sub n, is you want to sort of get rid of all the lower pieces and look at the quotient norm on L sub n. So this is some pretty technical sort of mumbo jumbo about how to put metrics on D Hodge-Tate of representations. But the nice thing about this is that the Lejeune construction, essentially what it does is it shows that this construction interpolates well in families. If you have a family of these sort of Hodge-Tate representations given by your local system, which you do in our case, then if you apply this construction of theirs, this p-adic Riemann-Hilbert construction, you get something which interpolates all the D Hodge-Tates, in fact, all the D de Rhams, but it doesn't matter for our purposes. And they show that the intrinsic norm actually defines an admissible height at P, which means it looks like what a V height should look like at P. They don't, of course, write things this way. They care about other portions. But you can show that what their construction does is show that things are fine at P. On the other hand, it's easy to show things are okay up to an additive constant, but it's hard to show things are sort of okay on the nose. And I'm not going to go into what that means. But basically, it's hard to glue this stuff across prime. This goes back to the original issue I mentioned with the O of 1 problem, where every prime here, you can show this kind of construction is nice up to a bounded additive factor, but you have infinitely many primes to deal with, so that's not good enough. Nonetheless, this sort of forms the foundation of what we do to make the canonical height. So we're almost done. We'd be done if this worked well. And here's what it would mean to work well. This isn't sufficient, but this is basically the idea. So here I've defined two intrinsic norms, two norms. There's naive norm, just which, oh, you can't see my pen. I'm sorry, I'm so used. Can you see my mouse by any chance? Okay, great. There's the naive norm, which just take everything from the metric on L. Look at the Hodge state, p-adic Hodge state decomposition, and look at the norm coming from L. Or there's the intrinsic norm, which says, no, do this more clever quotient thing. That's actually the more natural thing to do. Question: if you're unramified and crystalline and your weights are small, which are all standard assumptions of the subject, at least in that case, are these two norms the same? If we had an answer to that question, things would work a lot nicer than they do right now. But we don't. So we basically can't use this for all primes. We have to do something a little bit different. And this is where the final ingredient comes in. This is recent work of Eno and Groschning, which says more than, so essentially what Lou and Zhu prove is that these things you get here are Deram. This is why the sub dr. One of their main theorems is that the Galois representations coming from Shimura varieties are all Deram. Eno and Groschning upgrade that to crystalline at almost all places. And their method's very, very pretty. They have no idea. I mean, they knew about Shimura varieties, but their work had nothing to do with Shimura varieties. Their work is far more general. So all they need, the Shimura variety is a variety. It's got some integral model at almost all primes, because everything does by spreading out. And they use this duality principle one last time. They say that, look, if S is exceptional, well, they don't say this, they just use rigidity. But for us, if S is exceptional, everything is rigid. And what Eno and Groschning say is that if you have something rigid, then automatically you get something p-adically crystalline in the relative sense of Fontaine and Lafay, generalized by Faultings. A lot of technical stuff going on here. But essentially, if you have a good integral model and you have rigidity, which you always do for exceptional Shimura varieties, then you get a crystalline representation, and all this happens. This is shown by me and Pila and Shankar, but it's quite straightforward. This is all very compatible with Lou Zhu. Sort of all the different relative p-adic Hodge theories play well with each other. This is the only part where the restriction to properness comes in. Eno and Groschning is written only for proper varieties, and that's the only place in the proof where we need the proper assumption. At the moment, they have very kindly agreed to generalize their result to our setting for non-proper varieties. It's not yet finished, work in progress, but very, very hopeful that soon it will be done and we'll get the general theorem. Okay, that's all I had. I don't know if I went a little bit over. I'm sorry if I did, but thank you very much for your kind attention.
Thank you, Jacob. We thank Jacob for the very excellent talk. For the time, it's okay. Don't worry about it.
Okay.
Are there any questions or remarks for Jacob? So I was about to ask about the extension of the theorem from the proper varieties to the whole thing, but you already say something. So you're working with the new collaborators to achieve that.
Yeah, we're not doing very much. It's really them.
Okay. But we're getting there.
We're getting collaboratively, we're all getting there together. That's right.